I'm going to be talking about simple harmonic motion, and I'm really going to derive the equations for the two basic uh, devices that display simple harmonic motion. First, what is simple harmonic motion? It's really something that goes back and forth over the same path. You can see a pendulum. Pendulum swings back and forth over the same path to two extremes. And then a spring and mass, what happens is we set it in motion and it'll stretch out this way, and then it'll pull it back, and then it'll pull it back this way. So it's repeating over the same path, back and forth. The pendulum is going back and forth over the same path. And they're characterized by an equilibrium position. Okay, if this is frictionless, this is the place where it will naturally be, the normal spring length. I'm going to refocus. I hope. I'm going to try it again. That's a little better. So this was the place that would normally be. This equilibrium position for the pendulum is where the pendulum would hang if it weren't in motion. Okay, if there are no net external forces on it, it will be there. So a lot of things can be done with simple harmonic motion. Generally, the way we do it is we either give it an initial velocity, hit the pendulum or hit the mass, or we stretch it out to some farthest point, which is called the amplitude. So it's characterized by having an amplitude. And another characterization of it is that there is a restoring force towards the center. Towards the center. So if the pendulum is down here, there's no net force. It stays there. The tension would be equal to mg if it's not moving. Of course, if it's going through the bottom there would be a centripetal force if it had a velocity. But the farther it's pulled away, there is a net force towards the center, a restoring force, which is, in this case, it's really a component of mg. Over here, if we stretch the spring out, there will be a net force towards the center. The farther you stretch it, the bigger the restoring force. So the restoring force is proportional to the displacement, to how far it's been displaced. Okay, so those are the main characteristics. It's a repetitive force, or excuse me, repetitive motion. We're going to see that that this repetitive motion can be characterized with a sinusoid, with a sine or cosine curve. It has an amplitude. That's the biggest displacement. That's the amplitude there. The farthest place goes this way. That is the amplitude there. And it has a restoring force that's proportional to the displacement. Now, if you have not been taking calculus or you don't want to see where these equations come from, you can certainly skip the next part because I'm going to show you how we get the equations for the period and the frequency of motion for these things. Period being the time. These are two important things. Period. Time for one complete repetition. And the frequency. Frequency. Period, by the way, I'm going to put capital T is the symbol, measured in seconds. Frequency F is just how many number of repetitions per second, or hertz. Okay, so let me show you where that comes from. First of all, let me come back up here to the pendulum. I'll do the let me do the mass and spring first. Okay, at its farthest amplitude, well, at any point actually, the restoring force is going to be found by the spring. Excuse me. Let me pull this in. By this equation, force of a spring is equal to kx, and I'll just say that the amplitude of the force of the spring is equal to k times x, spring constant, times the displacement from equilibrium. Okay? And so we can use that with Newton's second law equation. Newton's second law equals ma. And if I call towards the center positive, then this displacement is going to be negative. Okay? So the force, oh man, let me put this different. If I let me do it this way. I'm going to be pushing that thing. So equilibrium is in that direction. I'm going to call that direction positive. So the force is negative k delta x, or x. I'll put delta x here. But the delta x would be negative here. It would be pushing in the opposite direction. Equals the mass times the acceleration. Well, if we get into calculus, the acceleration is the second derivative of the delta x. So what you end up with is negative kx equals m d squared x dt squared. Okay? I'm going to rearrange that so it looks like this. D squared x dt squared equals negative k over m times x. So the second derivative, the acceleration, is equal to a function of x. And the the functions that have that characteristic are sinusoids. If you think of a sine, the derivative of a sine is a cosine. The second derivative of a sine is negative sine. So we can see that same functionality here. And so it turns out that the function that fits this behavior, where the second derivative is proportional to itself but negative, is a sine curve. So let's do this. We're going to call this x equals sine of, and I'm going to call this thing omega times t. Okay? When x equals sine omega t, the dx dt is omega cosine of omega t, and the d squared x dt squared is negative omega squared cosine, sine of omega t. So you can see the second derivative here is some number, negative number, times x, times our function. Okay? So let's rewrite that. D squared x dt squared equals negative omega squared times that x. Okay, so it looks exactly like this, where omega is, remember this is omega, well let me just do it, negative omega squared equals negative k over m to match this up. So omega equals the square root of k over m. Okay, I'm going to stop with that right there. We've gotten an expression, the x equals sine of omega t, where omega is square root of k over m. Okay, I'll just write that. Square root of k over m times t. Okay, so we've got an expression. Now we can say this is the function that this spring and mass follows. Pendulum's a little trickier. Okay, pendulum, if I think of this, the restoring force, what we have is we have mg and we have tension. And the restoring force is the component of mg in that direction, perpendicular to the string. So the restoring force is going to be equal to mg times the sine of the displacement angle, theta. Okay? And if we call this positive, the force is in the negative direction. And this is going to be equal to m. And this is dx, d squared x dt squared. Well, you see we've got a problem. We're measuring one in terms of theta and one in terms of x. Well, since we don't have just a straight line perspective, I mean this thing's going to be curving, I want to rewrite this in terms of theta. And to do that, I got to do a little trick. Okay, and the trick is that I'm going to look at a little dx here, a little small x there, and that's going to be equal to this length times d theta. Okay, so this ends up being mass times length times d squared theta dt squared. And I'm also going to do a trick here. We're going to say for small values of theta, for very small values of theta, we call it the small angle approximation, then theta is equal to sine of theta. And you can do that, plug it in radians and see that we're really talking about below about 25 degrees, 20 degrees. So pendulum goes kind of well, it's already nonlinear, but it doesn't obey this if it's at large angles. But for smaller angles, this is going to be approximately equal to sine theta. So now look what we've got. We've got that relationship of theta and d squared theta dt squared. We can cancel out the m. Excuse me. And I can write it as d squared theta dt squared equals g over L theta. Okay, and I'm just going to do the exact same thing I did over there. When I use, again, understanding that this is going to be a sine function, I can make theta is sine of omega t, where omega is now square root of g over L. Just doing the same thing I did. Oh, I should have put the parentheses, another one. Got it wrong, sorry. T. Okay. So, what we've got is two expressions here. We've got theta for a pendulum, we've got x for a spring and mass. And the x is equal to sine of square root of k over m over t. That means bigger, well, we can plug in and we can find out at any time t where this thing would be. Same thing here if we know g and L. It only depends on k and m. Now the last thing I'm going to do is I'm going to write this, instead of omega equals square root of g over L, I want to put it in terms of f. Omega is in radians per second. F is in hertz, repetitions per second. And to get from radians per second to repetitions per second, we just divide by 2 pi. It's just a conversion. Square root of g over L. Over here, frequency is going to be, again, since omega was square root of k over m, this is just 1 over 2 pi square root of k over m. And then the final thing I'm going to do is I'm going to find the expression for period. Period is just the inverse of the frequency. So it's square root of L over g. Period of a spring and mass is 2 pi times square root of m over k. Okay, so these are the two expressions for period of a pendulum and a spring and mass. And if you look at the pendulum, the longer the length, the longer the period, the longer time it's going to take to get back and forth. The bigger the force of gravity, the faster. You can think of it's pulling more on that thing towards the center. The restoring force is stronger, makes it speed up towards the center faster. It decreases the period. Okay, so it depends only on L and G. And if you think of L, longer things tend to have a higher period, a longer period, and a smaller frequency. So I have long vocal cords. They take a long time to vibrate back and forth, but they give me a very low frequency. And we hear frequency as a note. So I sing low notes. People with smaller vocal cords, shorter vocal cords, everything else being equal, that tends to vibrate back and forth more frequently. They have higher sounds. Okay, that's how that works. Same thing over here. Well, I shouldn't say same thing over here. Over here, we don't have a length function, but we have the period depends on the mass. A bigger mass will make it harder to move back and forth. It'll make it more sluggish, more inertia. Bigger K means there's more restoring force. It gets it back towards the center. So these relationships, I definitely want you to internalize the general format of these things, and you should be able to reason through which of these is on top and which of these is on the bottom.